MathCounts friends. I hope everyone's having a great weekend. I thought I'd do another video where we go through a sprint test, and I am joined today by my son Kenton. Say hi, Kenton.
Hello.
All right, so Kenton is also interested in math, and he's pretty close to you guys' age. So I thought he might be helpful to have along for the ride today. So let's see. So first of all, these things that we're going to go over, that's all in the Google Drive. You should have a link to the Google Drive. If not, please send me an email. And you can go into Math Downloads. If you go to Sprint Round, we're going to do this 2014 State Sprint Round together. We'll go over some of the problems at least. We'll see how far we get. So I copied it in here, and let's see. Put it right up there. So let's see what we've got here. So let's look at the first problem, Kenton. What do we got here? The mass of a mouse is 25 grams. The mass of a small dog is 5,000 grams. The mass of the dog is how many times the mass of the mouse? How do we do this one?
Just divide.
Okay.
5,000 divided by 25.
5,000 divided by 25? Okay. 5,000 divided by 25. And what do you get?
200.
200, yeah. 200 is right. So that's because you can think of this 5,000 as 50 times 100. You know, if you split it here, and the 50 can be divisible by 25, you just get to 2. So it's 200, yeah. Is that kind of how you did it? All right, this says, what is the product of all the solutions to this equation? Do you know what that equation means?
X minus 3 equals 4.
Okay. What are these little, are there any confusing things here?
Yeah, I don't know what those lines are.
Okay, you don't know what these lines are. Yeah. You've probably never been taught that. Have you ever heard of absolute value before?
Absolute value? Does that mean like positive value?
Oops. Yeah, kind of like positive value. You take, you take the positive portion of it. Yeah. So you take the positive value of it. So if the absolute value of negative 10 would be 10, for example, the absolute value of 100 would be 100.
Yeah.
So you just make it positive. So these lines actually mean absolute value. So this is absolute value of x minus 3 equals 4. So what do you think?
So we could do negative 1 minus 3.
Okay, negative 1 minus 3 would give you, that would give you like negative 4, but then when you took the absolute value of that thing, it would just be 4. Okay, so x equals what?
Negative 1.
Negative 1. Is that the only solution? Because it says, what is the product of all the solutions?
No, you could do 7 minus 3.
Oh, okay, so 7 minus 3, that would also give you, that would just give you 4, and if you take the absolute value of this thing, it's still 4. So that's also a solution, so x equals 7 is another solution. So these, do you think those are all the solutions right there? Those two?
I don't see any other solutions.
Yeah, that's right. Basically, the way I think of it is x minus 3 absolute value equals 4. That means you're looking for some x that is like 4 away from negative 3. So if you think about the number line, right, you've got negative 3 here on the number line.
Mm-hmm.
And you want something that's 4 away from that. Well, you can either go 4 up this way, you get up to, oh wait, hold on. X minus 3. So it's not negative 3 actually, it's positive 3. I messed up there. So x minus 3 means the difference between that number x and 3, positive 3, is got to be 4. So sorry about that. So we start at 3 and we either go up 4, that gets us up to 7. Whoa, that's not much of a 7. Okay. Or we go down 4, and down 4 gets us down to negative 1. Here's 0 here. And there's our number line. Okay, so those are the two solutions. And what's the, oh wait, I forgot to put the 200 here for this one. What's the answer that we put here?
Negative 7.
Negative 7, because they want the product, which means you multiply the two together. All right, cool. Let's see. I think I know how to scroll here. Oh, not like that. Let's see. There we go. All right, so it says a square target has side length 16 inches. In the center of the target is a smaller square as shown with side length 4 inches. Okay, so we got 16 inches and we got 4 inches. If a dart randomly hits within the larger square, what is the probability that it will land in the smaller square? Express your answer as a common fraction. What do you think?
If we take 16 squared
Okay,
and 4 squared.
16 squared. What is 16 squared?
256.
256. And 4 squared?
16.
16 equals. Okay, and then now what do we do?
And so 16 over 256, which is just 1/16, I guess.
Okay, 216 over 256, which is 1/16. Yeah, perfect. So that is what? This is the probability that it will land in the smaller square. So 1/16, is that right?
Yeah.
Well, okay, let's put it 1/16. I think that's right. Now, one thing which I guess we don't have to worry about, but they should have probably said uniformly randomly, because randomly doesn't necessarily mean it's uniformly distributed, but that's getting into some real deep statistics stuff that probably they don't think they need to care about in MathCounts. But okay, let's move on to the next one. This one says circle P has diameter 2 centimeters. I think when they say circle P, that means that P is at the center of the circle. Okay. Circle P has diameter 2 centimeters, and what does this mean? M bracket thing like that, or whatever that angle thing is. What does that mean? Do you know what that means?
The angle?
Yeah, it's the measure of the angle, basically.
Yeah.
So the measure of the angle MPN. Where is the angle MPN?
If you look at M,
Okay.
and then you go down to P, and then you go up to N.
Oh, okay, so it's like here then, is that right?
Yeah.
Okay. So they're saying that's 120 degrees. 120 degrees. If the shaded region has an area k pi centimeters squared, what is the value of k? You got any idea how to do this one?
Not really.
Not really. Where do you think you could start? Do you think you could find the area of the whole circle?
You could.
What would the area of the whole circle be?
That'd be pi, I guess.
Pi?
Radius times pi.
That's right, it's pi r squared, and r is 1, so it's just pi. Is that right? R is 1? Yeah, because the diameter is 2.
Yeah.
So this is pi centimeters squared. I guess I could write the units of centimeters squared, or square centimeters maybe is a better way to say it. Okay, so that's the area of the whole circle. They're saying that the area of the shaded region is k times pi, and they want to know what k is. What do you think?
K has to be smaller than 1.
Has to be smaller than 1, yes.
And so...
What if they asked for the area of this part up here? Do you think you could figure that out?
Wait.
Like the white shaded part. They're asking for the gray shaded area.
Oh, I guess the white line gives... So you can figure out half the area of the circle.
Okay.
Right.
Yep.
So that'd be pi over 2.
Okay, so you're saying pi over 2 would be like this shape here if I went all around like this and straight across like that. That area would be pi over 2. Okay, so let's do that. This is pi over 2, which is equal to k times pi, where k is 1/2, right? But I'm not going to write that because that's not actually what k times pi is. K times pi is this part. So what do you think? Do you know what this whole angle is? Like, I guess all the way to here?
That'd be 180. So the whole angle of the circle would be 360.
Yeah.
So, wait, what is 120? Or 3, or no, sorry. 180 minus 160? And 60 plus 60 is 120. So both of the gray little sections is equal to the white section.
Okay, yeah. So you take these two shaded regions, add them up, you're going to get the same thing as this white region here. Yeah. Yep. Anything else?
So then you can say that if you take one of the white regions and split it in half and like rearrange the gray parts a little bit, then you know that half of the circle is going to be pi over 2, and that the gray regions are going to be 2/6 of the circle.
Okay, so we got 2/6 of the circle.
Yeah.
Okay, yeah, because we could cut each of the white regions into 2, and now you've got 60 here and 60 here. Actually, do we know what this angle is here?
That whole angle?
Yeah.
It's 120.
Yeah, it's 120. And there's two ways we could figure it out. We could either take 360 and subtract 120, and then subtract 60 and subtract 60, and it's got to be whatever's left, which will give us 120. Or we can just say, there's a thing called vertical angles, which says that whenever you have two lines that are crossing each other like this, if you know this angle is equal to, let's say, 57, then that means this angle is also equal to 57. And that's what we have here. So this is 120, that means this is also 120. And then if you know what this one is, you can say this one is also the same, basically.
Yeah.
And actually that's going to be 180 minus 57, because this whole thing is 180, so that'll be like 23 or something? Yeah. No. Yeah, 123. Okay. So you were saying that you've basically got 2 out of the 6 regions that are shaded now.
Yeah.
So it's 2/6 of the whole circle. And the whole circle was pi. So it's 2/6 pi. Is that true? That's the shaded area. They'll call it a shaded area. Shaded is 2/6 pi. So what do you think? Is the answer 2/6? It says it's k pi centimeters squared.
I guess.
Okay, the answer is 2/6. But in MathCounts, they don't like you to give answers of 2/6. Why not?
1/3.
Yeah, they like you to simplify it. So it's 1/3. So let's do 1/3. And you can also think about this. Oh yeah, that's 1/3, because you've got these two together is 1/3, and this top part is 1/3, and this bottom part's 1/3. So it's 1/3 of the circle. All right.
Yeah.
Cool. All right, let's take a look at this next one. So this one says, if f of x is equal to f of x plus 1 divided by 2, and f of 2 equals 4, then what is the value of f of 10 minus f of 7? I kind of drew over that part a little bit. I don't know if I undo a bunch. Yeah. Okay, you can hopefully read that. It says f of 10 minus f of 7. All right, what do you think? Any ideas how to do this one?
F equals 2, I guess, right?
Yeah, so what is this f? Is this f a variable or is it a function? You know what a function is? Did they tell you anything about functions? Okay. All right, so they haven't taught you about functions in school yet. So a function is basically like a black box, which can take in numbers and spit out numbers.
Yeah.
And so like it's like an input-output thing. So if you give it a 3, maybe it'll give you a 7. That's this function, f of x.
Okay.
Okay? And so what this is saying is that this function, I guess they're saying that if you stick some number plus 1 into the function and you divide it by 2, you'll get the same thing as just sticking that number into the function.
Okay.
So like if you stick 2 into the function, if you have this function f and you stick in 2, you're going to get out 4.
Okay.
And I guess from this formula we could say, oh, well, what if we stuck in the next bigger number, right? X plus 1. So that would be 3. If we stuck in 3, this formula tells us that f of 2 is equal to f of 3 divided by 2.
Okay.
And f of 2 is 4. So what do you think?
So 4 equals f of 3 divided by 2.
That's right. That's right. 4 equals f of 3
So could f
divided
be
by 2.
squared?
You're trying to figure out what the function is. Let's first just figure out what the function, what this f of 3 is. Let's start with that. What is f of 3?
It must be 8.
It must be 8. Okay, so now we know that if we stick 3, maybe I'll do that in a different color. So if I stick, if I stick a 3 into this function, what's going to come out? It's going to be 8.
Okay.
And now we could do that, well, I don't know, how are we going to figure out what f of 10 and f of 7 are? I mean, we figured out f of 3 from f of 2, but what do we do next? Any ideas?
We try to figure out the function.
Yeah, maybe. Maybe we could do that.
Or, wait. Would f of 10 minus f of 7 be equal to f of 10 minus 7?
Oh. So, like, that would be f of 3, you mean?
Yeah.
I don't think we can say that, for sure.
Okay.
Yeah, I don't think they gave us enough information here to say that. But maybe we could figure out what f of 4 is. Should we try that?
Yeah.
How would we do that?
I don't know. Wait.
They gave us f of 2, and we managed to figure out what f of 3 was.
Yeah, so
How did we do that?
we did f of x plus 1 over 2.
Okay, so if we set x to 2 to get this thing, right? What should we set x to try to figure out f of 4?
3.
Okay, so let's set it to f of 3. So f of x equal to 3, so f of 3 is equal to f of x plus 1, which is 4,
Yeah.
divided by 2. And we already know f of 3, right? What's f of
Yeah.
3?
It's 8.
Okay, so this is equal to 8. And now what's f of 4?
It's 4.
It's 4?
Wait, no. It's f of 3. Wait.
Yeah, I think you can ignore this part over here now because we put that equal to 8. So just look at this part over here. What's f of 4 if f of 4 divided by 2 is going to give you 8?
Then 16.
Okay, so f of 4 is 16, which means if I put 4 in to f, I'm going to get 16 coming out. All right, I didn't put these in the right order. I've got them going 2 in the middle, 3 down here, 4 up here. But anyway, you can see from the color. If I stick 3 in, I get 8 out. If I stick 2 in, I get 4 out. If I stick 4 in, I get 16 out. I guess I could write a table now. I could put 2, 3, 4. That is the x value. And the f of x value in my table, make my table like this. This would be 4, 8, 16. What do you think f of 5 is going to be?
It's going to be 32.
It's going to be 32, yeah, because when we stick f of 5 here, this is going to have a 16 here, and you're going to just be able to say 2 times. So basically it just means, yeah, actually we could just solve this thing for f of x plus 1. That's kind of a nice thing to do. We could say f of x plus 1 is equal to f of x times 2, right? So every time you go to the next one, you just multiply by 2.
That's nice.
Okay, so what do you think f of 10 minus f of 7 is going to be?
Oh. It's going to be 1024 minus 6. Wait, no, that's not right. Sorry. Wait, yes, it does. Wait.
Here's f of 5.
128.
That's correct. And what's that? Somebody figure that out for me. It's going to be a little less than 900, right?
Yeah.
It's going to be 4 less than 900, so that's 896. Okay. You think that's the answer?
Yeah.
896? I think so too. 896. All right, cool. So did it turn out to be the same thing as f of 10 minus 7?
No.
No, because f of 10 minus 7 is f of 3, which is 8. Okay. All right.
Yeah.
Cool. So it's a good thing we didn't try to do that. Okay. Let's go to number 6. It says if n represents the number of seconds in a day, what is the largest prime factor of n? Oh, do you think you could find the prime factor of the number of seconds in a day? The prime factorization? Do you know what prime factorization is?
Yeah.
Yeah?
I feel like that would take a really long time.
What is the number of seconds in a day?
It's like, I don't know.
I don't know either. Do you know a formula for it?
Well, if you did 60 times 60 times 24.
All right, 60 times 60 times 24. That's the number. We don't actually have to do this multiplication in order to do its prime factorization, though, right?
Oh, yeah, because if you just prime factorization each of those.
Yeah. And maybe one shortcut is, okay, look, I've got two 60s here. I don't need to prime factorize both of them, right? Because if the largest factor is in there, it's going to be in there. So let's just do one of them. Because all we care about is the largest prime factor of n. We don't even care what n is. So how do we get the prime factorization of 60?
We could do 30 times 20.
30 times 20?
No, sorry, 2.
Oh, 30 times 2. Okay. And then what do we got for 30?
3 times 10.
3 times 10. Are those prime?
Well, 3 is.
3 is. Okay, so we got a prime here, we got a prime here. We still need to break down
2
10
and 5.
into 2 and 5. Okay. Well, so far the largest prime factor is 5. Okay. So let's see if there's a bigger prime factor over here in 24. How do I break up 24 into two pieces?
3 and 8.
3 and 8. Are those prime?
3 is.
3 is prime. What about 8?
4 and 2.
4 and 2.
Or you could just go 2, 2, 2.
Or I could go to 2, 2, 2. But actually, they're already smaller than 5. So I don't even need anything else. I know 5 is the biggest.
Okay.
All right, so the largest prime factor of the number of seconds in a day is 5. That's cool. That one wasn't as hard as I thought it was going to be, right?
Yeah.
I don't know. Okay. All right, let's take a look at the next one here. So it says how many, I keep writing on the question. All right, how many convex polygons with an even number of sides are in the figure shown? Okay. Do you know what a convex polygon is?
Nope.
Do you know what a polygon is?
Yes.
Okay. So let me tell you about convex. Shapes can either be convex or non-convex. So let me show you what a non-convex shape would look like. See that shape?
Mm-hmm.
It's non-convex. Let me tell you how I know. I can find a point here that has all of its lines, all the lines that go through that point. So I'm going to draw a bunch of like yellow lines that go through that point. Okay, so there's one there. I'm not very good at drawing. Pretend all these lines go through the point. All the lines that go through the point also hit the shape, but it's not inside the shape. That means the shape is non-convex. How would you make the shape convex? Well, if you were to like change the shape so that it didn't have this little part in it, so it just went straight across like that instead, it would be a convex shape. Because every point you could find that has all the lines through it that hit the shape, they'll be inside the shape. There won't be any outside the shape if all the lines hit the shape. Does that make sense?
Yeah.
Okay. So for example, let me draw a polygon on here using these line segments that's non-convex. Like for example, if I went like this to here, to here, to here, to here, to here, that would be non-convex. See that? Because there's this area here. Okay. All right, so now we know what convex polygons are. How many convex polygons with an even number of sides are in the figure shown? So that one that I just drew had an even number of sides. It had 6 sides, but it wasn't it wasn't, did I say that wrong? It wasn't convex. It was non-convex. So we don't want to count that one. So what do you think? Any ideas?
You could find all the rhombuses.
Okay, you can find all the rhombuses. So there's a rhombus here, for example, right?
Yeah. And then another rhombus.
Maybe
Yeah,
here?
there. And then, let's see, how many rhombuses would that be?
There's 2 blue rhombuses.
1, 2. I mean, you could just make like each find a rhombus and find the opposite rhombus.
Okay. So here's another rhombus here.
That's
And it's
4.
got an opposite rhombus here. So we got 2 blue ones and 2 green ones.
None.
Are there any others?
Yeah, there's, if you go like one spot to the right of the green.
Here, why don't I do this? Why don't I give these things numbers? 1, 2. I'm going to give the triangles numbers. 4, 5, 6. So we've got a 1, 2 rhombus, a 5, 4 rhombus, a 2, 3 rhombus, a 6, 5 rhombus. What else we got?
A 6, 1, and a 3, 4.
6, 1, and a 3, 4. Okay, good. Do you think that's all of them? We got 6 rhombuses now.
E6? Wait. 1, 2. Yeah.
Yeah, I think that's all of them because every number in this circle, you can take that number and the 1 to the right of it, that makes a rhombus. So 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, and then 6, 1. Those are our six rhombuses. So we got 6 so far. Those are rhombuses. They have an even number of sides. Are there any other shapes that have an even number of sides that are convex?
Hexagon.
Oh, the hexagon itself, like the
Yeah.
big old hexagon like this, all the way around. Okay, so that's another one shape. Are there any others?
Wait.
So in order to have an even number of sides, it's got to have, well, it can't have 2, right? That doesn't make sense. You can't have a polygon with 2 sides. 4. Are there any shapes that are not rhombuses that are 4 sides in here?
Trapezoid?
Trapezoid, yeah. Trapezoid. Okay, so how many trapezoids could we make? First of all, are trapezoids convex?
Yes.
Yeah, those trapezoids, they're convex. So let's draw some trapezoids. We'll make them, probably should make them light
2,
blue.
3, 4.
Okay, 1, 2, 3.
Yeah.
Yeah. 2, 3, 4. Okay.
3, 4, 5.
3, 4, 5. Yep.
4, 5, 6.
4, 5, 6. Yep.
5, 6, 1.
5, 6, 1. Yep.
And then 6, 1, 2.
6, 1, 2. Yeah, basically
That's
each
6.
of these 6 numbers is going to be the middle of a trapezoid, right?
Yeah.
Okay, so we've got another 6 convex shapes. 6 convex polygons with an even number of sides. Those are trapezoids. Are there any other shapes you could make that are convex that have 4 sides from this?
No.
I don't think so. I don't think so. Okay. Alright, so we did 2 sides, which was nothing. We did 4 sides, which was 6 plus 6. We did 6 sides. Were there any other 6-sided figures that were non-convex? I mean, we could make convex, or I'm sorry, that are convex. We could make non-convex ones, right? We could, we showed an example of a non-convex, like this.
Yeah.
Or what about, like, I don't even know. This, I guess if we did 2 triangles like that, that's actually not a shape, right? Because it's,
Yeah.
yeah. So I think that's it. We got this number here. What's that?
13.
13. Lucky number 13, huh? Okay. All right. Consider the pattern of square grids shown.
Okay.
The sum of the number of square grids at stage 3 is 27.
Yeah.
Okay, you take the sum of all these, you get 27, I guess. If the pattern continues, what will be the sum of the numbers in the square grid at stage 7? So do you see a pattern here, first of all?
Yeah.
What's a pattern?
Well, at the bottom of each one, it goes 1, 2, 3, or 1, 2, or 1.
Okay,
1, 2, 4.
so the bottom row is just like 1, 2, 3, 4, or whatever.
And then the middle row is going to be 2, 3, 4, or 2, 3, or
2, 3, 4, 5, like
2, 3,
this.
4,
Yeah,
5.
okay.
Then 3, 4, 5, 6.
4, 5, 6.
4, 5, 6, 7.
4, 5, 6, 7. Okay, so basically it's just they're always increasing as you go to the
Yeah.
right. And they're also always just
Yeah.
increasing by 1 if you go up.
Yeah.
So in a way it's like, it's kind of like, how long would it take you to drive from here to here or something? You know, like,
Yeah.
like you would have to drive 2 spots to get up to here. Like, I don't know. Like, if, and then if I count like 1 more to get to the number, maybe it'd be like 1, 2, 3. 1, 2, 3, 4, 5, 6. Oh wait, I should have gone 1, 2, 3, 4, 5, 6, 7. You know, I don't know. That's one way to think about it. All right, so it says stage 7. So what's it going to look like in stage 7? There's going to be a big old square. You're going to have 1 down here. You're going to have 7 here.
Yeah.
You're going to have 7 here.
You're
Yeah.
gonna have a.
2.
What are you gonna have? And then there's gonna be a 13.
There's going to be a 13 up here, yeah.
I think if you want to find the one in the top right, you can just add the 2 on the bottom right, or on the top, yeah, on the top, and on the top left, and then subtract it by the number on the bottom left.
Oh, yeah, I think you're right about that. So you're saying you can take this number, and you can add this number, and then you can subtract this number, and you'll get this number. Okay. But they want the sum of the numbers in the whole grid all the way. So you've got, like here, you've got 1 1, you've got 2 2s, you've got 3 3s, you've got 4 4s, but then you've only got 3 5s, 2 6s, and 2 7s. Here we're going to have 1 1, we're going to have 2 2s, we're going to have 3 3s, we're going to have 4 4s, we're going to have 5 5s, we're going to have 6 6s, we're going to have 7 7s, then we're going to have 6 8s, and so on, down to only just 1 13. So I mean, we could add up all those numbers, but it would take a long time.
It's kind of like the way you roll, like a die.
Yeah.
If you're rolling 2.
Yeah, that's right. That's right. If you're rolling 2 dice, like if you're rolling 2 7-sided dice. I don't know what a 7-sided die would look like, but anyway, yeah, you would get all these.
If you could get like 1 on them.
Yeah, that's right. Yeah, like I guess if you'd rolled 2 7-sided dice and you subtracted 1, like this would be the sum that you would get, right? So like if you got a 1 and well, maybe one of the dice can go from 1 to 7, and the other die could go from 0 to 6.
Yeah.
And if you were to roll those two, if you got a 0 and a 1, you'd end up here at 1. And if you got a 7 and a 6, you'd end up here at 13.
Yeah. So you could just multiply 7 by 7, just square every. Well, no, not square every number. Do 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times
yeah, so that helps.
8 times 6.
That helps a bit, right?
Yeah.
1 times 1 is, well, except once you get past 7, you have to do
8 times 6.
8 times 6, yeah. So that would help. I wonder if there's anything. Yeah.
Well, if you, let's see.
Well, let's see. So I've got 1 times 1, and at the end I'm going to have 1 times 13, right?
Yeah.
And then I've got 2 times 2, and at the end I'm going to have 2 times 12. I wonder if I could like pair these up, you know?
Yeah.
So like I've got the 1 and the 13. That's 1 times 14. And then I've got 2 2s, and I've got 2 12s.
Yeah, so that'd be 2 times 14.
2 times 14. Okay, so I got 1 times 14 plus 2 times 14. I'm going to have 3 times 14. Oops, I didn't write that right. 14. All the way up to
7 times 14. Well, let's see. No, sorry, 6 times 14.
6 times 14. And then I'm going to have 7 times 7. Okay, cool. So I can simplify these ones by just saying what? This is 14 times 1 plus 2 plus 3 plus 4 plus 5 plus 6.
That would be... Oh, I should know this off the top of my head, but I don't. Like 16? No, sorry. 21.
Okay. 21. Good.
Yeah.
Good. So let's get into Python here. Let's see. So 14 times 21. 294.
294 plus 49.
Okay, so 294 plus 49. 343. Okay. Well, that's cool. Do you think that's the answer?
Yeah.
All right. 343. Yeah. that's cool.
Who's that Fibonacci down there?
Fibonacci? No, this doesn't look like Fibonacci quite.
It's,
Oh, is
so
it?
One.
It looks a little like Fibonacci.
Yeah, it like skips to 3
Yeah, yeah,
instead of going 1, 1, 2, 3, 4, 7.
yeah.
Or, no, not 4. 5. 8. It's like Fibonacci, but it skips to a 3. That's so weird.
You know, I'm noticing something about these sums actually. Before we go on to the next one, actually, this one, if you look at the sum, it's 1, and this one, if you look at the sum, is 8,
Yeah.
and this one, if you look at the sum, is 27, and this one, if you look at the sum, I think it is 128. Wait, hold on. Yeah, I think so. Do you notice anything about that pattern of numbers? 1, 8, 27, 128? Let's see, did I do that right? Oh no, it's not. It's not 128. It's 50. What am I doing?
No.
That's not right, actually.
Wait.
Let's see. 8. Is that right? It's 8. Oh no, 64. Sorry, 64. I meant 64.
I don't see any pattern.
You don't see any pattern? Okay, let me show you. 1 times 1 times 1 is 1.
Yeah.
2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. And 7 times 7 times 7 is 343.
Ah.
So, that's interesting, isn't it? I wonder if there's a nice way to think about this. Yeah, we'll have to give that some more thought, but I'm guessing there's a way to show that this is always, you know, basically n cubed.
Yeah.
So I'll have to think about that, but let's move on to the next problem for now. Maybe one of my MathCounts kids will figure it out. All right, consider the sequence 1, 3, 4, 7, 11, 18, 29, in which each term is the sum of the 2 previous terms after the first 2 terms. How many of the first 100 terms of this sequence are multiples of 5? Oh. So how do we do this?
Wow. If you just add the last number to the number that you had, to the last number of the number that you had before, you'll get the last number of the next number in the sequence. And we only need to know the last number.
Oh, I see. So you're saying you can just look at the ones digit, the units digit, right? So you got 1, 1, 3, 4, 7. The next one's 11, but you just need 1, and then you've got 8, something 8, something 9. So you can do this up to 100 terms and see how many of them are divisible by 5. Yeah, that's a little bit of a shortcut. It's a little bit of a shortcut, because if it has a 0 or a 5 on the end, yeah. Well, it still seems like a lot of work, but I guess we could try it. Okay, 7, 6, 3, 9, 6 and 3 gives you 9, 3 and 9, 2, 9 and 2.
Are any of them going to be multiples of 5?
Starting to look like, well, we haven't gotten any so far, so we're starting to get a little skeptical, huh?
Yeah. And then you're going to get 3, and then you're going to get 4, and then you're going to get 7, and then you're going to get 1,
Aha.
and then you're going to get 8, and then
We're
you're gonna get
repeating.
9, and then you're going to get 7.
Okay, so the answer?
0.
0. Okay, good. I was a little nervous when we were going to have to do 100 of these, but I'm
Yeah.
glad that we saw that it got to a repeating, and then we realized we were just going to end up doing the same thing over and over again. It's not, you don't, how many of these do you have to get to repeat in order to know that it's going to repeat? Like when I saw 1 here, I could have said, oh, it's going to repeat.
No.
No, why not?
Because you need to know two numbers that are the same as 2 numbers that you've already had.
Okay, yeah, because once you get this 1 and 3, it's the same as this 1 and 3. You know it's going to keep going. Okay.
Because you're adding the last.
Yeah, because all that matters is the last 2. Yeah. Okay, cool. All right, 3 different gifts were bought to be distributed to 3 children. Each gift box was labeled with the recipient's name. Unfortunately, the gifts were later wrapped, covering the labels. If each child is given one of the 3 gifts at random to open, what is the probability that no child opens a gift labeled with his or her name? Okay, so you got 3 gifts. Gift 1, that's more like a 6. Okay, let's say gift 1, gift 2, I keep writing 6s. I'm just too used to doing numbers because I'm a MathCounts coach. Gift 3, and then you've got child 1, child 2, and child 3, and they're going to get connected. Like maybe child 1 will open number 2, maybe child 2 will open gift 1, maybe child 1 will open gift 3, and maybe child 3 will open gift 2. For example, that's one possibility. But there are lots of possibilities. They want to know what the probability is that no child opens a gift labeled with his or her name. What do you think?
I think that's just 1/3 times 1/3 times 1/3.
1/3 times 1/3 times 1/3?
Yeah.
So what would that be?
Because there's a 1/3 chance that they will open their gift for each child, and so so you multiply those.
Okay. So let's say the first child comes along.
Yeah.
What's the probability of that child?
Or wait, no, that's not right. Well, yeah,
Let's- Okay, so let's say child 1 goes first.
Yeah. Wait, are they given at the same time? I guess it doesn't really matter.
Yeah, it's easier to think about if we just think about one of them going first, I think. But it doesn't really matter because...
Okay, so he has a 1/3 chance of getting his.
Okay, there's a 1/3 chance of getting his, but the question is the probability that no child opens a gift labeled with his or her
but if he
name.
gets number... So then child 2 comes along, and let's say child 1 took child 2's gift. He has a 0% chance to get his gift.
Yeah, that's right. So it depends which one child 1 picks, right?
Yeah.
So let's consider the 3 possibilities. So let's say child 1...
Well, if child 1 doesn't pick his, he has to pick one of the other person's gifts.
Yeah.
So...
Okay, so that is 2/3 of a chance, right?
Yeah.
2/3 of a chance that he picks somebody else's. And 1/3 of a chance that he picks his own.
Yeah. And so child 2, if the 2...
So actually, if this happens, we know... We don't need to think anymore about what 2 and 3 do because we know, in this case, that it's... that at least one of them got their own gift, right? Okay, so that's going to be, so our answer is going to be, our final answer is going to be 1/3. Oh wait, what is it that no child opens? Okay, so no, actually, the probability that somebody opens their own gift, well, maybe it'll be easier to figure out the probability that at least somebody opens their own gift, and then at the end we'll do 1 minus that. Does that make sense? Because those two probabilities have to add up to 1. The probability that no one opens their own gift and the probability that at least someone opens their own gift,
Yeah.
they have to add up to 1. So the probability that someone gets their own gift is going to be 1/3 plus something.
Mm-hmm.
All right, so we got 1/3 here, and then okay, so now we have to just consider this case is where child 1 picked one of the other gifts.
Yeah.
All right.
And then child 2 has a 1/2 chance of getting his own.
Well, it depends on if child 1 took
If
child 2's gift, right?
oh, yeah, that's true.
So let's
Well,
say
if child 1 gets his own.
Yeah.
No, that's not helpful. No, never mind. If child, it'd be 1/2 times 2/3.
okay,
Right.
1/2 times
Or no,
2/3.
1/2 times 1/3. So 1/6 of a chance, right?
Yeah.
Because
Well,
1/2 times 2/3 is just 2/6. And
1/2 times 2/3 is 1/3, right?
wait, yeah, exactly.
Okay.
So I think it would be 1/2 times 1/3. Or no, 2. No, well, if we're saying that child 1 got didn't get his own, then it's 1/2 times 1/3. And if we're saying that child 1 could have gotten his own, then it's 1/2 times 2/3. So if we want to know our final answer, then I guess we do 1/2 times 2/3.
Okay. So that's 1/3.
Yeah,
You're saying that's the final answer that goes up here? Or that's the final answer that goes...
the final answer that goes up, the first thing that goes on the answer line. If we want to get that, because
1/3?
because yeah, because we're saying he has a 1/3 chance, because child 1 has a 1/3 chance of getting child 2's gift, and he has a 2/3 chance of not getting child 2's gift.
Okay.
And so that means after child 1 gets his gift, child 2 has a 1/3 chance of getting his own.
Oh, I see.
Yeah.
Yeah, so that's just for child 2, though. But
Yeah.
so that's not the final answer that goes up here, right?
Yeah.
Let me see. Wait. Okay. So actually, I'm gonna go back a little bit. Maybe what I should do is write the 3 possibilities, right? So there's 3 possibilities. This child 1 can either get gift 1, he can get gift 2, or he can get gift 3.
Yeah.
If he gets gift 1, then we're done.
Yeah.
If he gets gift 2,
Then that means child 2 will have a 100% chance of not getting his gift.
okay, and what about child 3?
If child 1 gets, then child 3 would have a, if child 2 got child 3's gift, then child 3 would have a 0% chance of getting his
Right.
gift. But if he didn't, then child 3. So child 3, if child 1 picks child 2's gift, then child 3 has a 50% chance of getting his gift.
Okay. So I think in this case, there's a 50% chance that someone gets their own gift.
Yeah.
Okay. In this case, there's a 100% chance that someone gets their own gift.
Yeah.
It's child 1, at least.
Uh-huh.
Maybe some other people too. And in this case, where child 1 picks gift 3, what's the probability that someone's going to get their own gift?
50.
50%. Okay, and so these three things are all equally likely, right?
Yeah.
So we can just take the average of these.
Yeah.
That should be the probability that someone gets their own gift. So what's the average of
Okay.
these three?
That would be 200 divided by 3, which is something exciting.
2/3. 200 divided by 3 is 2/3, right?
Okay.
Or 200% divided by 3
Yeah.
would be 2/3. Because it's,
Uh-huh.
yeah, because it's like,
Okay. Wait, well, that's the chance that someone gets their own gift. So
oh
we
yeah,
want-
we want the opposite of that. We want
Yeah.
the, no, okay, so I gotta change this actually. So what is it? If the probability that someone gets their own gift is 2/3,
1/3.
the other, all the rest of the time is gonna be 1/3, and that means no one gets their own gift
Yeah.
1/3 of the time. Yeah, this is kind of a tricky one, right? I mean, actually, it might even be easier. Let me just show you another way to do it, which might even be easier, which sometimes, a lot of times you think this would not be a very easy way to do it, but in this case, I mean, in this case, you could just write out all the possibilities. Like,
Yeah.
you could get gift 1 and then gift 2, and then gift 3. Right? So I'll just write that actually even as just 1, 2, 3. Like, as the children come in, 1, 2, 3. Oops. That's not what I wanted to do.
Well, actually, it wouldn't be too
What did
hard
I
to write
do?
out all the possibilities. Because all you really have to do would just be like, if, wait, child 1 gets 1, child 2 gets 2, child 3 gets 3. Child 1 gets 1, child 2 gets 3, child 3 gets 2.
All right, so
And then
1, it could be
2,
1, 2, 3.
Could be
It could be 1, 3, 2.
It could
It could be 1.
2,
Oh, no, it can't be 1. That's the end of 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. So there's only 6 possibilities.
Yeah.
And then we could just circle the ones where no child opens a gift labeled with his or her own
Yeah.
name. This one is not one of those because actually everybody gets their own.
Yeah.
This one is not one of those because child 1 gets it. This one is not one of those because number 3 gets their own.
Yeah.
This one is 1. And
That one's
this
1.
one is 1.
And then
And this
that
one's not
one's
because
not
number 2 gets
2.
their own. Yeah, so it turns out that the only 2 possibilities is 2, 3, 1 and 3, 1, 2. So it's 2 out of 6. So yeah, it is 1/3 of a chance in the end.
Yeah.
Okay, cool. All right, good. We got through 10 problems. They're the 10 easiest problems, but we got through 10 problems. It's pretty good. Should we do any more? Should we call that good? What do you think?
I don't know.
You think my MathCounts friends are getting tired of listening to us? We could try one more. Should we try one more?
Sure.
Okay. This says the side lengths of 3 similar rectangular polygons are in the ratio.
Regular.
Oh, what did I say?
Rectangular pentagon.
Oh,
You
well,
actually
I
said
don't-
rectangular polygons.
Oh, I'm crazy. Okay, it's definitely time for me to quit here. The side lengths of 3 similar regular pentagons are in the ratio 2, 5, 7. The area of the smallest pentagon is 40 inches squared. What is the area of the largest pentagon? Okay, what does this mean? Do you understand this problem?
Are in the ratio 2, kind of. 40 inches squared. Not really.
Okay, let's look at all the terms here. Do you know what do you know what a regular pentagon is?
Yes.
What's a regular pentagon?
Pentagon with all the side lengths are the same.
Okay, so for example, if I did something like that, would that be a regular pentagon?
No.
But all the side lengths are the same. Well, at least I didn't draw it
all
perfectly.
the angles are
Oh, the angles all have to be the same too. Okay. All right, good. So a regular pentagon looks something like, I'm not the best artist here, but something like that. I didn't draw that perfectly, but you get the idea.
If you draw the little lines on each side, then you know.
Yeah, so you mean like this?
Yeah.
That way you know they're all the same
Uh-huh.
side length. And I also need to have all the same angles, right? So I can draw these angles and say they're all the same as well. We could actually figure out what that angle is, but I don't think we need to for this problem.
Yeah.
So you have side lengths of three similar regular pentagons are in the ratio 257. What does this mean, similar?
Means that if you like multiply the side length, let's say you've got a little square,
Mm-hmm.
then it would, and its side length was 2, then it would be similar to a square that has side length of 4 or 3. Since 4 is multiplying each side by 2 and 3 is multiplying each
What
side
if I
by
had
1.
a square that each side was pi? Would that be similar?
Yes.
Okay, so
I guess all squares.
all squares are similar.
And all regular.
All regular pentagons are similar, so they didn't actually need this word. I think it's just confusing. But anyway, they put it in there. All regular pentagons are actually similar. Okay. So the side lengths of three similar regular pentagons are in the ratio 257. So that means if you have one of these regular pentagons has a side length of, I mean, it's not necessarily a side length of 2. It might be a side length of 49, but it's the ratio between that one and the next bigger one, you know, is 2 to 5, right? So we could just,
Okay, yeah.
and then the ratio, the bigger one still is, well, I didn't do that right, but anyway, is 7, right? So you got 2, 5, 7. We don't know what the side lengths are, but we could just call this 2 units.
Mm-hmm.
And then it doesn't matter. It could be 49 centimeters, but we could just define a unit to be 49 half centimeters, and then 49 centimeters would be 2 units, and this one would be 5 units, which would be 5 times 49 over 2 centimeters, but that doesn't matter. This is 2 units, this is 5 units, this is 7 units. So we have these 3 pentagons.
Yeah.
And it says the area of the smallest pentagon is 40 inches squared. That's the area of this thing.
Yeah.
40 inches squared. And they want to know what the area of the largest pentagon is, question mark inches squared. So we just need to figure out what that question mark is. What do you think? Possible? Impossible? Hard? Easy?
That seems pretty easy.
Not super easy?
40 times 7.
40 times 7?
Yeah.
How'd you get that?
Because they're all making pentagons and... Or wait, no. So... Or yes. Yeah. Right? Because...
So you just take the area of this one and multiply it by the side length of this one?
Or no. Times 7 over 2.
Times 7 over 2?
Yeah. Because that's the... Like... The ratio between the...
Okay.
which
My
is-
MathCounts friends are watching this and they're trying to decide whether they think you're right or not. I don't know.
Am I right?
Let's try this with squares. Let's try this with squares.
Yeah.
What if you had a square that was 2 units and it
Yeah.
was 40 inches squared? Okay.
Each of those units would be
Now I've got different units here, right? So actually,
Yeah.
if it's 40 inches squared,
Or no, that would be, sorry.
if it's 40 inches squared, what? I don't know.
What are those units even?
Yeah, these units are not very good.
I don't like them.
I don't like them either. But anyway,
But if you're just pretending that they have 5 sides instead, then 2 something times 5. Wait, is that easier? Or no, that's hard.
this is hard because the square root of 40 would give you the side length in inches, but the square root of 40 is like
No.
not an integer for sure, right? It's like
Yeah.
2 times the square root of 10, which is, yeah, it's...
What about if you try to find...
Let's change it. Let's not use 40. Let's just use 4
Yeah.
for this square problem. Because that makes it really nice, right? 2
Yeah.
units and 4 inches squared. Now the units are just inches.
Uh-huh.
All right, and then let's say we go up to 7, right?
Yeah.
So
What side would
7.
be 7? Wait, that would be 49.
Yeah, 49. So is that 2 times 7 over 2?
No.
Because that would just be 7, but actually I got 49.
Wait, it would be 7 to the 7 squared, I guess.
Okay. So yeah, in this case that works because
Yeah,
the units are the same.
have
But
to go.
let's just think about it this way: what happens when you make a square twice as big? What happens to the area? What if you make the square, like the side length of a square, twice as big? What happens to the area?
The area was multiplied by 4.
Okay, yeah, that's right. So if you make, and what do you think happens if you take a pentagon and make
The
its side
area
length
is
twice as big?
multiplied by 4.
Yeah, the area is multiplied by 4, that's right. Doesn't matter if it's a square or a pentagon or a...
So you make it 7 halves as big, which means the area is multiplied by... Wait, you make it 7 halves... You make the side length, not 7, wait, yes.
Yeah.
3.5 times as big.
Right, right. You're making the side length from 2 units up to 7 units. We're making it 3.5 times bigger.
So
3.5 times bigger. So what's going to happen to the area if we make it?
you're
If
gonna
we make the side 3.5?
7. 40 times 7.
7. How'd you get 7? You did this this times 2.
Yeah. Or no. Yeah.
All right. I'm not sure that works because what if we make a square 3 times as big? What happens to the area?
The area. Oh. Okay. I see. So it'd be like 11.5 times as big or something.
How did you get 11.5?
I squared it.
You squared this?
Yes.
Okay, so
Or-
3.5
Yeah.
times 3.5.
Uh,
Okay, that is the right way to do it. What is 3.5 times 3.5 though? Let's see.
that's,
3.5 times
No, that's
3.5.
I think I did it right.
12.25.
12.25. That makes more sense.
Okay. So 12.2. So that means the area is going to
yeah,
get
I was doing-
12.2 times. The area is going to go from 40, and it's going to get multiplied by 12.25 times to get the area of this thing.
Yeah.
Is that right?
Yeah.
Yeah, I think that's right. So 40 times 12.25. Let's see. 40 times 12.25. 490. Point zero, yeah. We don't need the point zero. 490. Alright, cool.
Which is 70 squared.
It's what?
That's 70 squared.
Is this
Or
70
no,
squared?
it's
Not
70
really.
times 7.
Yeah, yeah.
Which I guess
Yeah,
I don't know
that's
why that is.
well, yeah, I think because like you can divide, if you divided this by 10, right?
Mm-hmm.
It would be 4 inches squared.
Mhm.
Just like, you know, we went from 2 squared up to 7 squared,
Yeah.
right? So this would go from 2 squared up to 7 squared, but now you're multiplied by 10 on both. So that makes sense.
Yeah.
Yeah. Basically, you're just taking this and you're multiplying by 7 squared divided by 2 squared, right? Because we multiplied by 3.5 squared. 3.5 squared is the same thing as 7 halves squared,
Yeah.
which is the same thing as 7 squared divided by 2 squared, which is the same thing as 49 divided by 4. You take 40, you multiply by 49 over 4. 40 divided by 4 is just 10, so 49 times 10 is 490. So I guess we didn't need to use Python to figure that out. We could have done it in our head if we did it with fractions instead of decimals. So yeah, squaring these decimals is not as easy as squaring the fractions. I mean, sometimes that's helpful. Okay, well, I guess I said that was the end for now, so let's quit. And I hope that my MathCounts friends enjoyed this, and if you like this, we'll do some more. Maybe we'll have Kenton here for our next video if you liked having him here. Did you like doing it, Kenton?
Yeah.
Okay. All right. Well, we'll see. Okay. Thanks, everyone. Have a good weekend. Bye.